We've learned about two forces already that act at a distance. We learned about gravity, which is always attractive, and we learned about electrostatic force, which can be attractive or repulsive depending on the charges of the particles that are involved. With with gravitational force, the magnitude of the force was dependent upon two things: the distance between the objects and the masses of the objects. With electrostatic force, it was distance and charge. What about magnetic force? Is magnetic force acts at a distance? Is it more similar to gravitational force or electrostatic force? And what are the similarities and the differences? Here we see two magnets being brought close to each other. Magnets have two sides. They have a north pole and a south pole. If we bring the two north poles toward each other, we can see that the one magnet is pushing the other magnet away. So we can conclude from that there's some kind of a repulsive force here. But look more closely. What else can you determine about that repulsive force? How does it relate to the distance between the magnets, and what other factors might be at in play here? Now, if we turn one of the magnets around so that the North Pole is facing the South Pole, then we see an attractive force. We see that as the one magnet moves closer to the other, eventually they get close enough that the attractive force is strong enough to overcome the frictional force holding that second magnet in place, and they actually snap together. And then once they're together, they hold together. So, what can you observe about the magnetic force between opposite poles, and what can you observe about the relationship of distance to force, or is there a relationship of distance to force? Now we see that magnets interact differently depending on their orientation. They can have the north to north, they can be oriented north to north, north to south, south to south, or they can be in some non well, they can be I guess parallel to each other as well, but mostly we'll just talk about the interactions between north and south poles. So let's talk about north to north, south to south, and north to south. In the first video, we saw that the magnet on the left moved away from the magnet on the right. What happened when they moved closer together, or what would happen if you pushed them closer together? Because if it moves away, if one magnet moves away from the other, they never really get any closer to each other than if they were. They never really get any closer together than they were when the one started moving away, when it overcame that static friction. And what would be different? Just think about this. What would be different if we had a lower friction surface, if it was easier for the magnets to move, or a higher friction surface, so the magnets were less likely to move away from each other? We talked about distance. Okay, gravity and electrostatic force both follow the same mathematical rule relating to distance. The distance, or I'm sorry, the force, excuse me, the magnitude of the force was proportional to the inverse square of the distance between the objects. What this means is if you double the distance, you get 1/4 of the force. If you triple the distance, you get 1/9 of the force. If you quadruple the distance, you get 1/16 of the force, and so on. This is what we call the inverse square law. Magnetism works the same way, as you probably observed. So the magnetic force follows an inverse square law, and there are other phenomena that follow inverse square laws as well, like light and sound. If you move twice the distance away from a light source, it's going to appear 1/4 as bright as when you are at the original distance. If you move 3 times the distance, it's going to appear 1/9 as bright. If you move 4 times the distance, it'll be 1/16 as bright. And the same is also true for sound. That inverse square law is a pretty good, um, pretty pretty good rule for determining intensity based on distance when something, a force or a source of energy, is spread in every direction. There are some fun things you can do with magnets. Like you can rub a magnet against a needle, as long as the needle contains iron. Most needles do. You can rub or some other, I guess not just iron, but some other substance that responds to magnetic fields. If you rub a needle with iron, it will become magnetized. And then if you float that needle on the surface of a cup of water, then the needle will turn and it will orient itself so that the magnetic field of that magnetic needle that you just made, it'll orient itself with the magnetic field of the earth. The whole earth has a big magnetic field, and uh, magnetic objects will, if they're free to move like a needle on the surface of water, they will orient themselves with Earth's magnetic field. This is how the earliest compasses were made. Now, if you put a couple of magnets under a piece of paper and then sprinkle iron filings on the top of the piece of paper, the iron filings are going to orient themselves with the magnetic field lines. Now, what is an iron filing? Iron filings are what you get if you rub a file against a piece of iron. Tiny little pieces of iron will break off, and those tiny little pieces of iron, they're not little spheres, they're not symmetrical, they are asymmetrical, meaning that they are wider than they are long. And so they make a bunch of tiny little bars. And because you have a bunch of tiny little bars, these are tiny little, when they're in a magnetic field, every one becomes its own tiny little bar magnet. And just like your compass needle orients itself with the magnetic field of the earth, the iron filings orient themselves with the magnetic fields of the magnets below this piece of paper. Now, which way do you think these magnets are oriented? Are they oriented north to south or south to south? Or are they oriented uh, are they oriented north to north or south to south, or are they oriented north to south? Is there an attractive force between them or a repulsive force between them? Well, here's another image, and this is oriented the other way. What do you think we're seeing here? One of these shows the magnets one of these shows the magnets with the north pole of one magnet pointing toward the north pole of another magnet. The other image shows the north pole of one magnet pointing toward the south pole of the other magnet. Which one do you think is showing an attractive force, and which one is showing a repulsive force? And what evidence do you have to substantiate that? Remember, north poles are attracted to south poles and repel other north poles. So one of these is north to north orientation, and one of these is north to south orientation. The green one is north to north, and the yellow one is south to south. I'm sorry, the yellow one is north to south. So on the green piece of paper, we have a repulsive force, and on the yellow piece of paper, we have an attractive force. Now, what evidence do you see from the iron filings that supports that claim that we have a repulsive force underneath the green paper and an attractive force underneath the yellow paper?